Okay, so I set up this problem, and what I want to know is how much of my force, my vector A, actually moves or acts in the same direction as the ramp, which could be thought of as a vector B. So if I rearrange these vectors a little bit, what I have is one vector, this guy, vector B, and another vector, this guy, vector A. And what I'm actually asking is, what is the projection of A onto B? So in other words, if I took this vector A apart, we would see that it's got two components. One acts in the same direction as the ramp, and the other one acts to kind of lift the object up off the ramp. All I care about is the part that acts in the same direction as the ramp. We're going to call this guy U. This guy would be V. So I've made a right triangle here, yes? And there's an angle theta. Remember that the cosine of that angle theta is related to the sides, the lengths of the sides of the right triangle, which is in turn going to be related to the magnitudes of the vectors. So in this case, magnitude of U divided by magnitude of A. So that means that the magnitude of my vector U is equal to the magnitude of my vector A times the cosine of theta. Now, anytime you see cosine theta in terms of vectors, and theta is the angle between the vectors, so anytime you see something that refers to the angle between the vectors, you want to think about the dot product. Because remember that the magnitude of A times the magnitude of B times the cosine of my angle theta is equal to A dot B. Yes? Yes. Okay. So that means if I divide this guy by a magnitude of vector B, I can find out that the magnitude of vector A multiplied by the cosine of theta is equal to A dot B divided by magnitude vector B. In other words, I can find the magnitude of the portion of A that acts in the direction of B from the dot product divided by the magnitude of the vector onto which we are projecting. Okay, so your textbook gives this a name. And what the textbook says is that they call this the projection of B onto A, except, yeah, okay. So this is actually the magnitude of the projection of angle of A onto B. So they call this the component onto B of A. Their notation is odd, but remember, the way that I remember this is that the vector I am projecting onto, so I am projecting A onto B. So A sits on top of B. Now, how do I actually write this in vector form? Well, if I wanted to write this projection in vector form, it's the magnitude right? Oh, I'm missing something. Oh, no, I'm not. Multiplied by a scaled version of b. So we would multiply this by the unit vector version of b. So we take b and divide it by its own magnitude. Which means what we end up with is a dot b divided by the magnitude of b squared. All of that, which is a scalar, it's just a number, multiplied by vector b. And your textbook calls this the projection of A onto B. Okay. So let's just take an example of how we would apply this. So I'm going to start, we're just going to do a simple example here. We're going to find the projection of vector 3, negative 2 onto vector 8, 6. So vector 8, 6. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. That's my endpoint of vector 8, 6. And I'm going to just call that vector b. And 3, negative 2. 1, 2, 3, 1, 2. I'm going to call that vector a. Now what I'm looking for, so I'm going to drop a vertical from A onto B. And what I'm looking for is that vector right there. That red guy is the projection of A onto B. Now, since that's hard to write, I like to just call that vector u, okay? But you can call it whatever you want. So the first thing we have to do is find that magnitude. So the magnitude, which your textbook calls the component of vector A projected onto B, remember, is equal to A dot B divided by the magnitude of vector B. So we have to do a little work first. So we need to find the magnitude of B. All right, so the magnitude of vector B, remember, is the square root of the x component squared plus the y component squared. In other words, it's the distance from the origin to the endpoint. So that is 64 plus 36. That's the square root of 100, so that is 10. All right, now the other thing I need is A dot B. So A dot B is the product of the x components plus the product of the y components, which is 24 minus 12, which is 12. So the component of A projected onto B is 12 divided by 10, which is 6/5. So that is the magnitude of this little vector that I sketched in red here. But what I really want is the vector notation for A projected onto B, which is given by your A dot B divided by the magnitude of B squared multiplied by vector B. So A dot B is 12, magnitude of B is 10, squared is 100, multiplied by my vector B. Okay, 12/100 scales to 6 over, or reduces to 6 over 50. And we remember from the last section that when we were multiplying a vector by a scalar quantity, we just multiply the scalar through the vector components. So we end up with 6 times 8 is 48 over 50, and 36 over 50 for 6, because 6 times 6 is 36. And those both reduce to 24/25 and 18/25 respectively. And that is the vector notation of the projection of vector A onto vector B. In other words, that is the vector notation of this little guide that I sketched right here. Okay, that is the projection of one vector onto another vector, and you would use this exact same work to answer that ramp question that I talked about at the beginning of this video. Okay, so one more topic in this section, and that is the topic of work, which turns out to be very important in physics, and so we'll come back to that in a second.